I'm going to start. Good afternoon, everybody. My name is Joan Solà. I work at the Institute of Robotics in Barcelona. And my topic is the Lie theory for the roboticist. I work in mobile robotics, navigation, state estimation, and control of different robots. And this talk is about some fundamental mathematics that are very useful for a lot of problems in which geometry is involved. So state estimation, I don't know, visual SLAM, controlling the robots, multi-link robots, everything related to poses, rotations, orientations, translations, changes of scale. Okay, all these kind of operations can be abstracted in a unified theory. And this theory is the Lie theory that I am going to target to the roboticist, in the sense that Lie theory is much larger and complicated that I will be explaining today. But I have made a selection of the key elements of this theory that are really useful for us. Okay, so Lie theory is quite abstract. Those of you who like mathematics, I think you will have the pleasure of getting into knowing all these tools. Those of you who don't like mathematics will probably have a hard time digesting this. It's difficult, although I made an effort to make it easy, but you will judge me at the end. Let's see. This presentation is quite graphical. There's quite a lot of drawings and explanations. And I try to make it as much intuitive as possible so you can get the ideas relatively quick, okay? So to start, I will start with a very simple example. And I will just start talking about the complex numbers, which you probably all know. Everything that I'm going to explain in this slide is probably well known for you, but the point is introducing Lie theory and introducing the key concepts that we're going to use. So as you know, in the complex plane, we can define points as, and interpret them as vectors in the y-i coordinate system, okay? And you also know that if I multiply two complex numbers, I get the result, another complex number, which is the same norm, the product of norms, and the sum of the angles. You know this. So if one of the complex numbers is unit norm, the result is that I am rotating the other complex number. Okay, so if I multiply the complex number x by a unit complex number z, the result is a new complex number y, which is a version of x rotated by an angle theta, which is the angle of z. Okay, this is quite well known. Okay, there should be no surprises here. But let's explore a little bit what's happening here. So the set of all unit complex numbers can be defined through a constraint. For example, z conjugate times z equal 1. This is just saying that the squared norm of z is 1, and therefore that the norm is 1. And so z is a unit complex number. And this constraint defines a shape on the plane, which is a circle of radius 1. So we can say the topology of this set of unit complex numbers is a circle. And we call this circle S1 because it's an abstraction of a sphere whose surface is one-dimensional, okay? So this is the sphere of dimension 1. It's the unit circle. The elements of this unit circle can be written like that. Z equals cosinus theta plus I sinus theta. Okay, no surprise. Theta is the angle of this complex number, and it's also the angle by which this complex number is able to rotate other complex numbers. Okay, so x becomes y by rotating theta radians. All right. We can define an inverse for this complex number, which is z conjugate. It would be a symmetrical drawn under the real line at angle minus theta. Okay, that can be written by z conjugate. And we can compose different operations by using the complex product. Okay, so you can look at the complex plane as just the complex plane and just have numbers x, y, zeta there. But because the unit complex numbers belong to a subgroup of this plane, we are going to separate these two entities. The unit complex number z, we will interpret it as an operator that is able to transform other numbers of this plane. So, Victor, can you see my pointer on the screen? Hello?
Let me check. Move it, Joan.
It's on the top right of the screen now.
No, we cannot see it. Wait a minute, it's not normal because normally we used to see it.
That's a pity. Anyway, okay, so I know, yeah, so I will not be relying. No problem. So look at the first line on the right. So I draw the z in blue, and because it has a particular properties written on the bottom of the screen, we will treat it as an operator which acts on x. Okay. In this case, z and x have very similar forms, but this is not the case in all Lie groups. Okay. So we are interested in this course in talking about the operators of the type z. And we will move away from the unit complex numbers and talk about other kinds of objects that behave in the similar way. For example, let's see what happens also on the plane. We also want to rotate vectors x to produce vectors y, but we want to use this, we want to do it now using just the rotation matrices R. So you see that now the operation y equals r times x. It's performing the same rotation over x to produce y, but the operator now, instead of a unit complex number, is a rotation matrix. Okay. Let me play a little bit with this animation. Okay, so by multiplying x by r, you rotate x. This is well known. And so we can build the same properties as we did for the complex numbers. So the constraint over r is r transpose times r equal to 1. Very similar if I go back to the constraint I wrote for unit complex numbers, z conjugate times z equal 1. Now we have r transpose, excuse me for this, r transpose times r equal 1. Okay, the topology is also a circle, but now we have to be a little bit careful because r are 2 by 2 matrices, and what does this mean to be in a circle? So if you write the plane in which these things happen as the real axis would be the identity matrix I, and the vertical axis will be skew symmetric matrix, whatever it's called, 1x, I will explain later. So in this plane, all the rotation matrices R define a circle. And so we can call this a circle SO2. The elements of this group are I cosinus theta plus 1x sinus theta. And this product gives you the typical rotation matrix is cosinus of theta minus sinus of theta, sinus of theta, cosinus of theta. Okay, the inverse is built with the transpose, and the composition is just the product of rotation matrices, as you all know. Okay, so it works basically if you abstract a few things. Basically, if you extract the algebraic operations, you get the same kind of properties for this group of operators called SO2, the rotation matrices in the plane, and the group of also rotation matrices in the plane, but constituted by the unit complex numbers. So there's a lot of similarities. Lie theory is the theory which will abstract all these operations and build a unified theory for all these objects. Okay. As I said, we will separate these two types of elements. In this case, it's very clear because on the right you can see vectors, x or r times x are vectors. On the left you see matrices. R is a matrix. Okay, so we will separate these two sets of elements. The sets of elements on the left are called Lie groups. Okay, and Lie groups are able to act on other elements, in this case vectors, to produce transformations on these elements, in this case rotations. Okay, so it's two different things. One thing is the set of operators, that is the Lie group, and the other thing is the space or the elements onto which these operators operate. Okay, in this case are vectors, right? So this separation is quite pertinent. Let me now change to a new group, which is the unit quaternions. They are used in robotics for 3D rotation, the same way as 3D rotations matrices are used, but quaternions. And in this case, if I were to write or to draw actually the rotated vectors in the same space as the Lie group of the quaternions, I would not be able to make this drawing in the same place. So I am obliged to separate these two spaces, right? So in the case of complex numbers and rotation matrices, I could still draw all the things in one unique drawing, but in this case, this is no longer possible. So yes, quaternion Q is able to rotate a vector x by performing the operation Q times x times Q conjugate. And this will rotate x by an angle theta if Q is defined as, now look on the left, Q equal cosinus theta half plus U, which is a unit vector, it's a direction in space, times sinus of theta halves. Okay, just to say that separating the Lie group elements from the elements that are to be transformed by these Lie groups, it's a good thing to do. Let me talk about a new Lie group, which is called SE2. This is the group of rotations and translations in the plane, and it's used to for transforming reference frames in the plane. Okay, it's usually represented by a 3x3 rotation matrix, which contains the 2x2 rotation matrix, 2x1 position vector P of t, and then 0, 1 at the bottom. So the abstraction here, I'm going to play a very short animation now. It's to see that what happens when a point moves on the surface of this Lie group is that the representation of this movement of a point in a surface is the same thing as moving, for example, a robot in the plane. Okay, so while the robot changes position and orientation, there is a point moving on a certain surface, abstract surface, which represents the pose of this robot at any moment. Okay, the same thing we can do, for example, in SE3. Now consider a humanoid with a lot of links. Each link can move in 3D space, can change orientation and change position. So each link of this humanoid robot can be represented by an element of SE3. And you can see on the left that these elements, each one of them is a point on a surface. Okay, this surface is defined by the constraint defining the group. Okay, remember that when I talk about the topology of the unique complex number, which is a circle. So each Lie group has a particular topology, which is defining a surface in which all their elements are living. Okay, I usually represent these surfaces as spheres, but sometimes it's difficult to recognize a shape. Okay, sometimes these surfaces are more than 3-dimensional. In the case of SE3, these surfaces are 6-dimensional. So I cannot really draw them on the board so that you can see them, but you can say, okay, this is a surface, 6-dimensional, and there is a point moving in this surface. and okay, you can, I think, understand the idea behind this little animation. Okay, that's the whole point of unifying all Lie theory in one theory. Okay, so why Lie groups? So Lie groups are powerful because we use them as transformation objects. We can rotate and translate. We can change the scale. We can produce skew transformations. We can do many different transformations to many different objects. And for each one of them, each one of these kind of transformations, we can identify a Lie group. And then each element can have an invert. We can compose them. We can interpolate linearly between different elements of this kind. These elements can act on elements of other sets. And then up to here is more or less what I explained in examples. But things go a little bit beyond and become interesting when you realize that you can now build a theory to produce, to do calculus on these objects. Calculus means basically doing derivatives and integrals. Okay, everything which relates to the infinitesimals is calculus. So now we can define integrals, differentials, and so we can deal with uncertainty. We can deal with small increments and this kind of thing. So we can start thinking about state estimation, for example. There is noise, uncertainties, small errors. We can talk about control. So you have a little error between the measurement and the reference, and then you compute an error vector, and then this, maybe you want to pass it through a controller to produce some comments for motors. Okay, but some of these measurements or desired state or whatsoever can be, for example, orientations in 3D. So we need a way to work properly with these objects. Okay, so once you are able to understand all these kind of operations in an abstract form, then you can apply it to each one of the particular groups, and you become very, very, very powerful. I mean, you have a full understanding of everything, and you can jump from 2D to 3D, from rotations to rotations and translation, and you have all the tools to work properly in any of these domains. So you become like a little bit more powerful than before. Maybe before you knew some rotation matrices here, some quaternion over there. You didn't make the links that make these two things equivalent. Okay, so once you have this new understanding, you can use it for estimation, planning, control, probably also learning, or anywhere you want to use it. Okay, so that's the interest of going into these kind of theories. Okay, for example, this is a small table with the Lie groups used typically in robotics. So on the first line, you have just vectors of Rn, which can be used for translations. This is just trivial. Okay, no big issues here. In 2D, we can have rotations by using the unit complex numbers S1, the rotation matrices SO2, and you can use rigid motion, which means rotation and translation, with SE2. In 3D, you have the three equivalents. So the 3-sphere S3 is the group of quaternions, and it's pretty much equivalent to the complex numbers, but in 3D. Then you have the rotation matrices SO3, which act similar to the rotation matrices in 2D, and so also the rigid motions. Okay, in this table, you have a lot of properties. You have the size of the space, the dimension of the Lie group, the type of elements, the way to define the constraint for these elements, and then a number of notions, Lie algebra, tangent space, exponential map. These kind of things are proper to Lie theory, and is the kind of objects that the kind of concepts that are going to be explained in this course. Okay. So so far this was just a presentation. Okay, so that you know what it's all about. And now I'm going to start, let's say, the matter of the course. Okay, so we will give a definition of what's the Lie group. We will also define the tangent space. This tangent space has two forms, Lie algebra and the Cartesian form. We will talk about the exponential map, which is a way to pass from the group to the tangent space. And we will define a number of operators that will allow us to enter the world of calculus, okay? So derivatives, uncertainty, integration. And we will end up by presenting an application for localization and mapping. And I don't think I will make the example about sensor self-calibration because that would take too long. But localization and mapping we will talk about. Okay. So let's go. So what is a Lie group, or what is a group actually? Because a Lie group is a particular kind of group. So a group is a set of elements that we can name X, Y, Z, together with an operation that we name it here with a dot, such that the composition of these elements is also in the group. You can think now of, for example, unit complex numbers, okay? X and Y would be two different complex numbers. If you multiply them, the result is a unit complex number, okay? The identity, so there's an element of this group that when you multiply it with other elements, this other element gets unchanged. In the unit complex plane, that would be E equal the number 1. If you multiply by 1, things don't change. There's an inverse. If you multiply the inverse by the element, the result is the identity. And then the fourth property is that this operation must be associative, okay? So that a number of properties that later on will appear can be guaranteed, okay? So these four axioms are the ones defining a group, okay? It is very important to say here that the operation dot in most interesting Lie groups is non-commutative, okay? So X times Y is not the same as Y times X, all right? You know this for example, in 3D rotation matrices, you know that you cannot change the order of the rotations because the result is another thing, okay? However, for example, in 2D, you can change the order of operations, okay? Rotations in 2D are, let's say, very much trivial. Actually, you can represent them by just an angle, okay? And so you know that if you rotate 45 and then 30, it's the same as rotating 30 and then 45, okay? Because you can sum the angles, and the sum is a commutative property. But you cannot do this kind of trivial operations in 3D, okay? Right, so what is a Lie group? So a Lie group is a group, right? So it's a set of elements with an operation that fulfill the four axioms that is also a smooth manifold. And that means, very intuitively, that all these elements live in a kind of surface. We call it manifold, right? And this surface is smooth. It has no edges or spikes, okay? The definition of a smooth manifold, we can go through the mathematical definition, is, let's say, more involved, but it's not necessary to go beyond this intuitive notion. So the surface, n-dimensional surface, where the elements of the group live, it's smooth. So it's a kind of surface similar to the one on the left in blue. Okay. Also, put otherwise, we can say that a Lie group is a smooth manifold whose elements satisfy the group axioms. Okay. First, we said that the Lie group is a group that is also a smooth manifold. You can put it in the reverse order. You can say the group is a smooth manifold whose elements satisfy the group axioms. Actually, the first definition is the classical one. And in the last years, the definition of Lie group has been changing to this new definition, but it's the same thing, okay? So important for Lie groups, which has been also already introduced before, is that they can transform elements of other sets, okay? We call this the group action. So what is the action of a rotation matrix? So it's rotate, okay? What is the action of a rigid transformation matrix? So it's rotate and translate, okay? So that's the action. And the action also has a couple of axioms, which are very, very intuitive. So if you act with the identity element of the group, then the element that you want to transform is unchanged. That's very easy. So the identity matrix times any vector gives the same vector. And this operation is compatible with composition. So you can compose X and Y to act on V, or you can act on V first with Y and then with X, and the result must be the same. All right? Okay. And okay, that's it. Actually, this action is quite central in the group, in the Lie group theory, to the point that the beginning of this theory, which dates back to the late 19th century, this is an old thing. This theory was started with the name of continuous transformation groups. Continuous because of the manifold, and transformation groups because the notion of action was central from the very beginning of all this theory. Okay, so let's talk about the topology of Lie theory. So I told you at the beginning that this is quite geometrical, and actually we can draw quite a lot of things that involve Lie theory that are visible geometrically. I like a lot geometry, so I prefer to explain things geometrically than in hard mathematical formula. Okay, so I told you that the Lie group is defined by a smooth manifold, and this smooth manifold has a certain shape. In this case, I draw a blue sphere. I hope you can see it properly on screen because of resolution. I think it's visible. So this blue sphere would be the manifold, which is defined by the constraint of the Lie group. Remember, the constraint in the complex plane was unit complex vectors. So that was a unit circle. You can imagine the constraint of unit quaternions. Quaternions are elements with four coordinates. That's why they're called quaternions. And they are unit norm. So you can imagine that this defines a sphere of radius 1 in the space of 4 dimensions. Okay, maybe I cannot draw it easily, but if I remove 1 dimension, that would be the drawing you see here. That's a sphere in 3 dimensions. So you could imagine there is a sphere in 4 dimensions, but it's a sphere. So that would be, for example, the manifold of the unit quaternions. Okay, in this manifold, there is a particular element which is the identity. All right, and in this particular element, and exactly touching the manifold in a tangent way, you can define the tangent space. Okay, the tangent space at the identity is called the Lie algebra of the Lie group. So you have the Lie group, which is the blue part, and the Lie algebra, which is the red part. And what is key and interesting and marvelous of this theory is that this Lie algebra, because it's a tangent space, is flat. It's a linear space. It's a linear vector space. All right. So many things that are difficult to do in the manifold because it's nonlinear and it's curved and has funny shapes are easy to do in the tangent space because it's just a vector space. So you just go to linear algebra when you operate on the Lie algebra. All right. And for example, all the material of calculus is performed in the Lie algebra. We will see how we do that. Okay, let's keep going with the topology. So imagine in this Lie algebra, in this red plane, you can define vectors that you can see as these straight lines departing from the identity, from the origin. And so these vectors are tangent to the manifold, of course. And what happens is that if you roll these vectors onto the surface, imagine this vector is a piece of string, and you roll it onto the sphere, all right? And so for example, the red straight line has the same length as the red curve, which is rolled over the sphere, okay? So you have a tangent vector that you can transform into a group element by rolling it onto the surface, following what we call the geodesic, which is the great arc. So you don't roll it doing strange, funny shapes, but just in a straight line. All right? This operation, going from the Lie algebra to the group, is called the exponential map. We will see how it works. And of course, you can do the opposite. You can go from the Lie group to the Lie algebra by unrolling it. And this is called the logarithmic map. So it may be surprising that exponential and logarithm appear here, but that's the way it is. I will explain in a few minutes. And the operation of going from the algebra to the group is really an exponential, mathematical exponential. We will see how it works. Okay. So let's talk a little bit about the tangent space. So just a few basic ideas. Because the manifold is smooth, it means it has no edges or no spikes. At any point x on the manifold, you can define only one tangent space. All right? This is a consequence of the manifold being smooth, is that every point has a unique tangent space. Also, these tangent spaces have the same structure at every point. Okay, for example, if you have a sphere and you put a plane tangent, this plane is a two-dimensional plane. So all the planes on the surface of a sphere are two-dimensional planes. So they are all the same space, put in different points, but the same space. Okay, the tangent space is a vector space. We can do calculus on it. We will see that, and I already said before. The dimension of this tangent space equals the number of degrees of freedom of the manifold, because you are obliged to move on the manifold. If you put a tangent space there, the dimension of the tangent space is the number of degrees of freedom that you have on the manifold. Okay, and already said, that's a little bit of terminology. The precise tangent space touching the identity point on the manifold is called the Lie algebra. All right. Okay, so let's talk about the tangent space of S1, just to ground these concepts a little bit. Let me play this animation for a second time. So if you have a point moving on a unit circle, okay, it has to move on this circle. And so the velocity of this point is a vector tangent to the circle, right? The velocity of z, it should be z dot, but here is z prime, but it's z dot. There's the derivative of z with respect to t. It's tangent to the circle. So in linear algebra, if you have a point x and you derive it with respect to t, x dot belongs to the same space of x, right? If you have a 3D vector x and you differentiate it with respect to time, the velocity of this vector is another 3D vector, okay? But this does not apply here, right? So z dot does not belong to the space of z. In particular, z dot does not need to have unit norm. Okay, you can have zero velocity, so that's a vector of zero norm, and of course, it's not a part of the unit complex numbers. Okay, and this velocity, when you put it at the origin, it's because it's tangent, is a vertical vector, and therefore it's an imaginary number. You can write it as I times omega. Okay, omega would be the rotation rate, and because it's imaginary, you multiply by I. So how do we go along in discovering the structure of the tangent space? Let's write the constraint of this Lie group, z conjugate times z equal 1, and differentiate with respect to time, and develop a little bit. You find that the second line of this set of equations, z conjugate z dot equals minus z conjugate z dot conjugate. You see that the element z conjugate z dot is equal to minus its own conjugate. Whatever z is, this product is always minus its own conjugate. And in the complex plane, all the numbers that are equal to minus their conjugates, if you think a little bit about that, they must be imaginary numbers. Okay, if you conjugate an imaginary number, you get minus the number, right? So it's mandatory that every element z dot z conjugate z dot is in the form I times omega. Okay, and this is the form of the Lie algebra. Okay, the Lie algebra is I times omega, and when we abstract the notation for Lie algebras of any group, we use this hat marker. Okay, we will write omega hat equals I omega. Okay, and this omega hat will always be an element of the Lie algebra. Of course, we can say, okay, why do we bother representing this with an imaginary number if all of these elements are imaginary and they only depend on one parameter, which is omega? So if we know that this is an element of the tangent space, we can just call it omega. We know that it's going to be I times omega, but we can work just with omega. Okay, and so this tangent space has two representations. Let's say the proper one is the Lie algebra, but we can find an equivalent representation, which is the Cartesian, and you can always go from one to the other very easily. So omega hat is I times omega, and the opposite omega is omega hat v. V is the opposite of hat. You see that one is a triangle pointing up and the other points down. And so you can go from one representation to the other very easily. This operation is linear. It's usually quite trivial, so it doesn't involve anything. And you can now express elements of the tangent space, in this case, through real numbers. Okay. Let's see another group where this kind of considerations will become a little bit more interesting. Okay, in the really considering a real number or an imaginary number is not a big deal, but it will be a big deal in other groups. Let's go, for example, to SO3, right? That's the group of rotations in 3D. Okay, you know, this is a bit more complicated. Let's take the constraint as we did before. Now the constraint is R transpose times R equals Y equals I, sorry. Let's differentiate with respect to time. And we find the following: R transpose times R dot equal minus R transpose R dot transpose. So again, what happens here is that an element, R transpose R dot, whatever this is, for any R, is equal to minus its own transpose. Before it was minus its own conjugate. Now it's minus its own transpose. It's not the same thing. But again, the only matrices in 3x3 matrices which are equal to minus their own transpose are the skew symmetric matrices. And skew symmetric matrices can be written like this, like the matrix you see here, with 3 zeros on the diagonal and anti-symmetric entries on the off-diagonal positions. Okay. In particular, when at the origin we have the Lie algebra defined by omega cross, that I am now on the bottom line. So omega cross is the skew symmetric matrices matrix defined in this form. Okay. And the interesting part comes now. So you can see that this matrix, the skew symmetric matrix, you can write it as a linear combination of 3 coordinates, the omega x, omega y, omega z, multiplied by 3 constant matrices, which you can identify as a certain base to define the space of skew symmetric matrices. Okay. The important thing here is that we have 3 coordinates, and therefore we can represent the same tangent element with a 3D vector with these 3 coordinates. Okay, so we have the Lie algebra representation, which is a skew symmetric matrix omega cross, and an equivalent representation, which is omega, which is a 3D vector. And now you can see that omega as a 3D vector is much simpler than omega cross. Okay, and this has a number of advantages. If you have 3 or 4 or 5 or n of these elements, you can stack them in a longer vector. So you can start thinking about a state vector for a particular robot, which not only contains omega, but other things. If everything that you want to represent can be represented with an equivalent, which is a vector, then you can stack everything in a long vector and then start thinking about, I don't know, control schemes or estimation engines, because everything will be a vector. So this double representation is very, very interesting. Okay, again, we have a trivial linear transformation from one representation to the other. So the hat, omega hat, is equal to omega cross, and omega is omega cross V. So these are the two linear transformations from one tangent space to the other, from one representation of the tangent space to the other representation. That is one tangent space, two representations. All right. It's getting involved. I told you this is not necessarily simple. I hope you follow. I think at this point, if anyone has a question and want to stop me, that could be a good point. So stop me at any time, and because I think if somebody starts getting lost, I would like to recover you at this point before going on. Okay, I will go on, but please stop me if you want. All right. So now we have understood what kind of elements live in the manifold of the group. So we will have rotation matrices, unit complex numbers, quaternions, this kind of elements. And what kind of elements are living on the tangent space? There will be weird elements such as imaginary numbers or skew symmetric matrices, which can be represented as plain Cartesian vectors. Okay, and there is a clear transformation from one to the other. We can transform tangent elements to group elements with the exponential map, and we can do the opposite operation with the logarithmic map. All right, so let's see here. I want to play this animation 2 or 3 times. So imagine you have rotation matrix RO2, an object which is rotating at constant rotational speed. So its orientation will be represented by a rotation matrix in SO2 in this case, and the velocity of this rotation will belong to the exponential to the tangent space in red. Okay, so the angle theta cross of t, the angle theta of t, will be omega times t. So you can see that as the angle progresses in the tangent space, the rotation progresses in the group. Okay, again, so that's what happens when things change continually in time at constant speed. Okay, so how can we, let's say, show the relation between r of t in yellow, and theta cross of t in red? There must be a relation between these two elements. One is in the tangent space, the red one, and one is in the group, the yellow one. There must be a relation. You can see it here. There must be a relation. Okay, so let's see. Let's write r transpose r dot equal omega cross. Isolate r dot from this equation. R dot equals r times omega cross, and this is an ordinary differential equation that we can integrate. You can integrate this by doing exactly this operation. R of t equals r0 times exponential of omega cross t. If you differentiate this expression, you find the expression on top. So that's the integral. Okay, and we already have the exponential map here, just by mathematical integration of the differential equation. Okay, now if for example r0 is the identity, as in the drawing, we started at the identity, we have that r of t is the exponential of omega cross t. And if omega cross t, we call it theta cross. That means the omega t would be the angular velocity times time. And the cross means we are in the tangent space in the Lie algebra of the group. And we can multiply omega times t and get an angle, and that would be theta cross is also an element of the tangent space. And to go to the group space, so to get the rotation matrix R, this is the exponential function. So how do we find an expression to compute this exponential? Very easy. We express the Taylor expansion of the exponential. We define it like this. So you know that the Taylor expansion is identity plus the element plus 1/2 of the element square plus 1/3 factorial plus times the element cube and so on. And then you realize that I is the identity matrix, and 1 cross is the skew symmetric matrix. Actually, it's not written in this board, but it would be 0, -1, 1, 0. Is this matrix, okay? And the powers of 1 cross, if you multiply 1 cross squared, gives you 0. And if you multiply 1 cross cube, gives you -1 cross, and so on. So you can group all these elements in terms of I and 1 cross. And you find these parentheses, 1 minus theta cube, 3 factorial, and so on. And each one of these two series are the series of cosinus of theta and sinus of theta. So you get I times cosinus of theta plus 1 cross times sinus theta. And if you group these two things together, you get this matrix, cosinus theta minus sinus theta, cosinus theta. And this, as you all know, this is the rotation matrix into D. Okay, it has been obtained by doing the exponential of the skew element theta cross. Okay, all right. So that's how you get the exponential map and a closed form for this exponential map. I will not develop the logarithmic map. You can find the inverse of this operation with probably using the arctangent and these kind of things. All right, so the exponential map goes from the Lie algebra to the group, and the logarithmic map goes from the group to the Lie algebra. Okay. In this case, we use theta cross. That means we are in the Lie algebra. We said before that we can represent elements of the tangent space by Cartesian vectors. So we can very easily find theta cross from theta and define a new exponential that notice that I wrote it with a capital E, which englobes these two operations, passing from the Cartesian representation of the tangent to the Lie algebra representation, and then doing the exponential. These two operations together are represented by a capital exponential. So you pass from theta to R with exponential of theta, and from R to theta with logarithm of R. Okay. All right. And yeah, you pass from theta to theta cross like this. So a little bit of a map of transformations. You have on the left the tangent space with two different representations. On the top is the Lie algebra. On the bottom is the Cartesian form. You have the hat and V operators to go from one to the other one. These are linear operators. And then from the Lie algebra to the manifold, you have the exponential and the logarithm to go back. And the capital and exponential and logarithm are shortcuts to perform the two operations. For example, capital exponential is the normal exponential of the element. So first you apply the hat operator and then the exponential, and you get the capital exponential, and vice versa. These capital operators are shortcuts. There's nothing new, but they are just useful. So because they relate vectors to group elements directly without taking care of what happens in the Lie algebra form, which is always more complicated. All right? So new operators that we can define here and that will bring us to the calculus part are the plus and minus operators. So the plus operator, if you have composition, which is usually a product, and the exponential, you can combine these two things together. To do what? To say, okay, I have an element x, and I have a velocity and an element tangent to this, and I want to know what's the new element. Okay, so you want to combine an element of the group with an element of the tangent space of the group to get a new element of the group. So if you exponentiate omega, you get exponential of omega, and the result, you compose it on top of x, you get x times exponential of omega, right? And just by definition, there is no invention here, or no discovery, or no any new concept. It's just a definition. We will express this composition as with the plus operator, and we will put a round around the plus, so that it's not mistaken with the regular sum between vectors. Okay, but now that's important. You can in any way add a vector on top of an element of the group. If I say it in other words, you can add a vector to a rotation matrix. That's kind of weird, but this vector would be, okay, I have a rotation matrix. I want to add 3 degrees in a particular direction to this rotation. This 3 degrees is a Cartesian expression, so you can add them by using this plus operator. And of course, you can also define the minus operator, which would be the difference between 2 elements of the group, for example, the element y minus the element x, and you want to express this difference as a vector of the tangent space. Okay, so that's the difference would be x minus 1 times y. That would be an element of the group that goes from x to y, and then you take the log to put it onto the tangent space, and you get a vector. All right. So plus and minus are opposite operators, and they are also shortcuts. Okay, they don't introduce any new concept. They are just shortcuts. But now see that we can add and subtract things, and that's going to be very interesting. Before entering to calculus, because now we have plus and minus, so calculus is going to be there very, very quickly. Let me, so from the plus and minus operators that you see here, let me introduce a new element of Lie theory, which is a little bit abstract, but imagine you have a manifold M. This is a smooth surface, whatever. And you have the identity element, which I call it here with the capital epsilon on the left, okay? And we have an element X of this group, all right? So the transformation in green, which goes from the identity to the element X, is just the same element X. That means E times X equals X, of course, because E is the identity. And then you add on top of X the tangent vector tau, all right? So the element Y is X plus tau, is X times the exponential of tau, all right? But you can also get to Y following a second path. That means taking a tangent element at the identity and then composing with X, right? So you have that, you can get to the point Y by doing either sigma plus X or doing X plus tau. And because these operations are not commutative, sigma and tau are not the same, not equal, okay? But they must be related somehow. There must be a relation between sigma and tau, so that if you do one operation or the other operation, you get exactly to the same point, Y, okay? And this relation between sigma and tau is called the adjoint. So it's actually linear. And because it's linear, if you represent sigma and tau as vectors, the adjoint is a matrix, okay? If tau and sigma are Cartesian vectors, and there is a linear relation between them, this relation can be expressed with a matrix, all right? And this matrix depends on the point x, because it's the only variable here that is involved, okay? It's a linear relation, and it depends on x. It's called the adjoint matrix at x. This is going to be used later. But it's central in Lie theory. So if you are interested in going into Lie theory for any reason, you will find the adjoint. I found in the literature that this adjoint is defined in very strange ways that are completely non-intuitive. So that's why I give you this vision of the adjoint, which I think is intuitive enough. All right. Okay. So it's linear, and it maps elements of the tangent space at x. We call this Tx of M. The tangent space of M at the point x, so Tx of M. It maps Tx of M to Te of M. So it maps elements of the tangent space at x, so elements of the type tau, onto elements of the tangent space at the identity. That is the Lie algebra, which I call it in this case sigma. All right. Okay. Let's go to calculus. Let's go to calculus. Imagine you have a manifold M. That means the manifold of a Lie group. The elements x and y could be, let's say, 3D rotation matrices or quaternions or rigid motion matrices in 2D on 3D, whatever. Let's just to say something grounded. Let's say these are 3D rotation matrices. You have one rotation matrix called x, and you have another one which is y, which let's say is close to x. And then y minus x is a vector that expresses this difference between x and y. Okay? If x and y are relatively close, you can say that this is an error that you can have on your knowledge of a certain matrix x. So you have, for example, a measurement of this that would be y, and the reality is x. So y minus x is the error, for example. Okay? Or it's like an increment between one and the other one, whatever. The important point is that these errors, increments, perturbations, these kind of notions that are not necessarily infinitesimal, but they are usually small. It's good to express them in the tangent space, because then we can define Jacobians and covariances to manipulate these elements to go from one tangent space to the other one, propagate covariances through nonlinear functions. All these kind of things are easy to do if the perturbations are expressed as elements of linear spaces. Okay, so let's see, for example, what happens in a vector space when you define, for example, a Jacobian matrix of a function f of x. Well, you take the limit when h goes to 0 of the function f of x perturbed by a perturbation h minus f of x divided h. And this is an n times m matrix, the Jacobian matrix. Actually, this matrix stacks all the partial derivatives of f of x with respect to each one of the components of x. Okay? Okay, how can we export this or adapt this to Lie groups? Okay, so we just substitute the sum by a plus and the difference by a minus and write this formula. So this means that the differential of f of x with respect to x can be defined in the same way. So we perturb x, okay, with a vector tau. We compute the difference of this perturbated result f of x plus tau. We compute the difference with the original f of x, and we obtain another vector because we use minus. And then we take the limit as tau goes to 0. And then now we get a Jacobian matrix, which is going to map elements of the manifold of x at the point x, elements tangent to that, vectors tangent to the manifold at the point x, to vectors tangent to the manifold at the point f of x. this operation of mapping is going to be linear, and it's a Jacobian. So the space of departure is a linear space, is the tangent space at the manifold of departure, and the space of arrival is also a linear space because it's also the tangent space at the arrival. Okay, there is a drawing later on. So how do we compute in vector spaces these derivatives? So we write the expression f of x plus h minus f of x on the numerator. We manipulate it until we get some linear form, jh, and then because it's divided by h, this just by the identification, we identify the Jacobian J. I say this because you can actually not divide by h. This is undefined. H is a vector. You cannot divide things by vectors. But this way of proceeding is rigorous, and it's practical enough to work. So you just manipulate the numerator until you get a linear form, and then you just eliminate h and get the Jacobian. You do the same thing in the groups, okay? So f of x plus tau minus f of x is this weird formula on top, logarithm because of the minus, of f of x minus 1 because of the minus, times f of x exponential tau, and x exponential tau is the plus operator that we defined before. And so you write this, you start manipulating these expressions, and then up to the point that you get j times tau divided by tau. And then the Jacobian is j. This looks super complicated. It's not. It's usually very quick to do and very easy. Okay? Let's do an example. Imagine you have a function that takes an element of SO3, that is a rotation matrix, and a vector in R3, and produces a vector in R3. And this function is just a rotation. Okay? So f of Rp is R times P. That's a P rotated, an amount indicated by R. All right? So what is the Jacobian of F with respect to R? First of all, R is a matrix. So this is the Jacobian of something. F of R is a vector with respect to the matrix. But this is just a notation. What we want is a Jacobian with respect to R, but infinitesimal variations around R that are expressed in the tangent space of R, which is a 3D vector. Okay? So we express the limit, the definition. You have the definition on the top right. We just particularize it here in this case. So x plus tau becomes R plus theta, all right? And f of x plus tau is R times theta times P. The minus becomes just a regular minus because the space of arrival is R3, and the minus operator in R3 is a manifold, but it's a trivial manifold. So the space of arrival, the minus here is just a regular minus. Now, for example, you can expand exponential of theta to the first term. So the plus is a real plus because we are in SO3, but the minus is just a minus because we are on R3. And then a couple of ideas. The exponential can be approximated by the Taylor expansion, I plus theta cross. And then you develop these things, and you get minus R times P cross. That's the Jacobian of F with respect to R. Okay? It's not that difficult. There's a little of things involved, but it's not that difficult. The Jacobian of the same function with respect to P is much easier. Okay? You perturbate P. Now P is a vector, so you perturbate with a regular plus, and you do the same things. And very, very quickly in this case, you get R delta P divided delta P. So the Jacobian is R. Okay? And in this case, both plus and minus operate on the vector space R3. So they are just regular sum and difference. Okay? So now we are able to compute Jacobians only groups, and these Jacobians relate tangent spaces, okay, from the departure space of the function f to the arrival space, but always the tangent spaces. So this is a true Jacobian matrix. Okay, a little drawing here that I don't know if it's going to be clear or more confusing. I'm not sure. But what we did is that we have, on the left, we have a manifold M, where the elements X live. That's the departing space of the function f of x. In the example before, this was SO3 for the rotation matrix. And then we have a arrival space N, which in the example before was R3, is the rotated vectors space. And so perturbating the matrix R was adding, for example, tau 1 with the operator plus. In green, you go to the manifold with the exponential and with the plus. And then you apply F, you go to the right manifold with the green arrow, and that's F of the perturbated matrix. And then you apply the minus operator, and you get the difference in the arrival space. And then you take the limit when the perturbation goes to 0. So you take this red curve, approach the point f of x, and in the limit, you get J1, which is one of the columns of your Jacobian matrix. Excuse me for this drawing. If I can be interactive and pointing things is more easy to understand. But anyway, let's go on. All right, differentiation rules. We have defined the differentiation, and it's good to know that for each group we can define a number of blocks that are fixed for that group. For example, the adjoint. We know a formula for the adjoint. We can define the exponential of the derivative of the exponential, which we call right Jacobian, and the derivatives of the action. Okay, this need to be defined for each individual group. Then we also have that inverse and composition have these forms for all groups. So the derivative of the inverse of an element of a group with respect to itself is always minus the adjoint of the group. So that's good to know the adjoint, because now you have, for all groups, you have that the derivative of the inverse is minus the adjoint. Likewise, the derivatives of the composition with respect to each one of the terms is either the adjoint of y minus 1 or the identity. And this is true for all groups. It's good to know, okay? Doesn't matter if you are working with quaternions or with complex numbers. So this is always true. And so you can deduce from these formulas more derivatives, the derivative of log, the derivative of plus, minus, and these kind of operators. And for any other thing, you apply the chain rule, which works, okay? So to compute the derivative of R transpose P with respect to R, well, you just break it into pieces, apply the chain rule, and you get this formula. R transpose P, everything cross. That's this Jacobian. It's easy, it's powerful, and it works for all the groups. So it's good. We are almost finished. Nearly the last point I want to talk about is perturbations. So now you have a manifold M in blue, and with a element x bar on it, and you express perturbations around this element with tangent vectors tau. Okay, and so if tau has a certain I like this. If it has a certain uncertainty, so you obtain this ellipse on the red plane, on the tangent plane. If this is a perturbation, a Gaussian perturbation, you obtain like this ellipsoidal shapes. Okay, and you can map this shape onto the manifold through the exponential map, and you would have a notion of what's the perturbation on the manifold. This is just the exponential map rolling this plane onto the surface. Okay, each one of the points there can be brought to the surface through the exponential map. Okay, so it's good to define a perturbed element x as x bar plus tau. And if we define the covariance of tau as the expectation of tau transpose, the expectation is the typical operator to define moments in probability theory. So now expanding tau as a function of x, you get that this is the expectation of x minus x bar times x minus x bar transpose. And this minus is the minus we defined for the Lie group. Okay, this formula is the same, except for this minus form as the formula you use to define covariances in linear spaces. You just use a regular minus sign. Okay, here you just substituted by this O minus sign, and you get a perfectly usable formula for covariances. And if you want to propagate this covariance through a nonlinear function f of x, well, you have the Jacobian that we presented on the previous slides, and you just propagate it exactly as you do in linear spaces. So you multiply left and right by the Jacobian. The right is the transpose, and you get the propagation of this covariance through the nonlinear function f of x to obtain a covariance on the point y. Okay, that's very, very useful. The last notion is integration. Integration in the sense that I want to integrate velocity into movement. Okay, for example, angular velocity into rotation matrices or whatever. Okay, so maybe I didn't say, but the exponential itself is the continuous time integration of omega onto the velocity expressed in the tangent space onto the manifold. Okay, but in this case, the integration if omega is constant. Okay, the differential equation only has the exponential as solution if the velocity is constant. Okay, so for non-constant omegas, we just divide all the trajectory of omega in piecewise constant elements, and then we use the plus sign to concatenate all of them. So integrating motion is simple. That's a good way to go. If omega is constant, which you can assume if the time interval is very small, usually you say, okay, the velocity in a delta t is constant. And then at different delta t's, I allow the velocity to change. And then I use the piecewise formulation on the right. Okay? Okay, so far, theory. I hope you're not dead, or at least that some of you are still alive and interested. I'm going to give you...
Sorry, John?
Yes?
You have a comment on the chat?
Oh, sorry, I didn't see them. Many of them? Sorry.
Yes, one comment by Florian.
Okay, let me read this comment. Okay, could you show the previous slide? Okay, I will go to the previous slide, of course. Yeah, I hope it's this one. Can you confirm me? Is this one, or you talked about the
one previous.
Number 31? Okay.
Yes.
Okay, this one. Is there a particular question about this? If you can write it on the chat, and Victor, if you can read it for me, because I don't see it on the screen. Or maybe I can switch if the user is keen to put the question, or otherwise I just show it for a while or explain it again. I will explain it again. So you have a manifold in blue, a point on it, which you can, as always, imagine this is, for example, a rotation matrix, and you have a perturbation on this matrix that you want to express as a vector. Okay, in this case would be a 3D vector. I didn't say, but this is very important. If you have a 3x3 rotation matrix, it has 9 numbers. Okay, if you perturbate these 9 numbers, the result is not a rotation matrix because it's not unitary, it's not orthonormal. You killed the properties of the rotation matrix. You can only modify a rotation matrix in 3 directions. And all of these directions belong to the tangent space. That's why when you move tangentially to something, you keep on the surface. Okay, that's very important. And that's why if you move on the tangent space, you always stay on the surface. I mean, you move on the tangent space and then you apply the exponential and you go back to the surface. Okay, But you have to move in these 3 degrees of freedom. You cannot move in 9 degrees perturbation. That's just an error. That's a mistake. This is not good. Okay. Same with quaternions. You have 4 coordinates. If you perturbate the 4 coordinates, the result is not unitary. You can only perturbate 3 coordinates. No, not 3 coordinates. 3 degrees of freedom, because the last degree of freedom, which would be the norm, you're not allowed to change. Okay. The tangent space guarantees that the operations you do when you perturbate in this way, because of the exponential that always goes back to the manifold, so you always guarantee the constraints of the manifold, and therefore you stay on the manifold. This is very important. Okay. So yeah, you define this perturbation as tau, and then the covariance as the covariance of tau. You express it in terms of x. You obtain this expression p equals expectation of x minus x bar, and so on, which, if you are more or less used to covariances in linear spaces, this formula would remind you of the formula of the definition of the covariance, just with the signs changed. And then propagation is just easy. It's just the same thing you do in vector spaces by propagating covariances through nonlinear functions. But you use the Jacobian left and right, multiply, and then you get the new covariance. Okay, that's about this slide. Integration and an example. This example is actually 2 examples. The first one is map-based localization using an EKF. So we will have a robot moving in 3D space. This is represented by these triangles. Okay, the robot at time 1, at time 2, and at time 3. And we will have a number of beacons, or sometimes called landmarks, in space. And because this is map-based localization, we will consider now these beacons are known. Okay, if they were unknown, that would be SLAM, simultaneous localization and mapping. But because they are known, it's map-based localization. The only thing we want to estimate is the position of the robot at any time. Okay, so the state of the robot is a Gaussian variable belonging to SE3, that is position and rotation in 3D space. And the covariance is, as we said before, the expectation of x minus x bar, and so on. Okay, to build a Kalman filter, we need a motion model. And this motion model is the composition of the state of the robot times its velocity per time. Okay, so if you are somewhere and you have a certain velocity, after delta t, you are somewhere else. Okay, and this somewhere else is expressed by the integration that I presented on the last slide. Okay, and so the comment, the control signal is a certain input ui times delta t, and then plus w. W is just white noise, is the perturbation on the controls, which is a Gaussian variable with covariance q. I'm not going to explain Kalman filter. I know that many of you maybe don't know Kalman filtering, but I cannot explain Kalman filter in this course. Okay, so sorry for those of you who maybe this last minute of my presentation will be completely non-understandable. But those who have played a little bit with Kalman filter will find it interesting. Okay, it's just a couple of minutes. We also need a measurement model, and in this case, we will measure. Imagine you have a sensor on the robot that is able to measure the location of the beacons in the reference frame of the robot. Okay, so because the beacons are expressed in the global reference frame, we have to transform them to the robot reference frame, and this is done through the action of SE3 on the points in 3D. Okay, and because we're going from global to local, we have to invert x and apply this action, and then we have a noise v. So that's the measurement model. We will have measurements of the positions of the beacons in the robot coordinate frame, and with a noise v. And this noise v has a covariance r. It's a white noise with covariance r. So prediction. We will take the mean of our state vector, and we will integrate the controls and not the noise. So this is our prediction. This is our function x hat equals x hat plus ui dt. And we obtain the two Jacobians of this function with respect to x and with respect to the noise w. And then we integrate the covariance by using the same formula we use usually in EKF. So we take these Jacobians, the covariance of P, we propagate it to the new position after the prediction. Okay. For the correction, we take the measurement model, we compute its Jacobian, H, and then we obtain the innovation, Z, which is the difference between the measurement Y and the expected measurement X minus 1 BK. We compute the covariance of this innovation, HPH transpose plus R. We compute the Kalman gain, PH transpose Z minus 1. And then we produce the update, X plus KZ and P minus KZ K transpose. Okay, that's a Kalman filter. If you know Kalman filter, you will find these formulas super familiar. The important point here is that to compute the covariance, we use Lie theory because of this minus. To integrate, we again use this theory because of this plus. And so the covariance is well defined. It has the right numbers of degree of freedom. And the integration is also well defined when you integrate on this operation. The result is always something on the manifold of SE3 because this plus sign guarantees that. That's the tangent velocity. We also use the inverse using the theory. We use the action here to compute the measurement model. And then we use the Jacobians as we defined previously. We update using the plus so that when we compute KZ is a certain update step which belongs to the tangent of X. So we compose it with X with a plus sign so that the new X, which is an element of SE3, completely nonlinear, can be updated with a vector. That's super cool. Okay. The rest of this slide contains formula of EKF, which is completely standard, no surprises. Okay. Second example, let's do SLAM now. Let's also estimate the positions of the beacons, but let's use a least squares method on the manifold in what is called graph SLAM. Okay, so the poses of the robot again are in SE3, position and orientation in 3D space, and the beacons are point in 3D, which are unknown. And we use the state space, which is I call it the composite of different Lie groups. So our state space is formed by X1, X2, X3, which are SE3 matrices, B1, B4, B5, B6, which are 3D vectors. You cannot stack this in a vector because 3 of these elements are matrices. The other 3 are vectors. Okay, and we pose the following least squares problem. So the optimal X is the X that minimizes the sum of all the residuals, and the residuals are P, and these residuals are defined by each one of the measurements. So we have a residual for the prior. The prior says that X1 is located on a certain reference, X1 reference, with some uncertainty omega1. Okay, the motion residual computes the error or the discrepancy between the control signal for motion, UGDT, compared to the actual motion between I and J. So xj minus xi, okay? And the measurement residual, it evaluates the discrepancy between a measurement of a beacon and the theoretical measurement given the state, x minus 1 times b, okay? So you put all this in a big matrix, all the Jacobians, and so you obtain the Jacobians of the residuals, you put them in a big matrix. Again, I'm not going to explain nonlinear least squares estimation, but this is the way you go. And then you compute a Newton step, the delta x, and you compose it with the old x with the plus operator. So delta x is a vector, x is a set of manifolds, and you can define a plus operator so that the new x obtained after the update is perfectly on the manifold. And this you iterate until the residual gets very small, and then you finish. Okay. Important again here is that we use plus and minus everywhere that is necessary, and that the Jacobians are computed following the guidelines of Lie theory. Right? I think that's all I have to say, except that I hope you like that. And if you want more information, we have I don't know if now it's 17 or 18 pages. It's a paper about everything that I explained in the same spirit of being didactical and so on. We produced a C++ library for all these operations, which is called Manif, which works the same way as the Eigen library. It's also based on Eigen at the base. And we already have, I don't know, we have SO2, SO3, SE2, SE3. We have translations on the plane. We have an IMU group. So there are a number of groups there. More groups can be contributed. Then we have a cheat sheet with a lot of formulas that you can find in this link. And on YouTube, you will find a couple of courses similar to this one. One of them, the one in the link here, is the one I gave last year for this summer school. It's a little bit longer and it has a little bit more explanations, but it's pretty much the same thing. And that's it. So thank you very much. This last comment on the bottom, it's residual from another talk, so don't pay attention. Just read the top line. Thank you. And if you have any questions, I will be happy to help you.
Thank you very much, Joan. Thank you very much for this presentation.
Okay. Just give me a minute to plug my adapter, okay? Because I'm battery.
We don't have time enough for a feedback session, so I think you can write Victor or me with any comment about the summer school. We have not finished, as you know. Yeah, at 3 o'clock we will receive Yanis Demirik from Imperial College of London. So I think it's a really very interesting talk. Don't forget that we continue during this afternoon, and need to tell to you that we are open to your comments and your feedback by email, because if not, you don't have time for your lunch time. So thank you very much. And it's all. We wait you at 3 o'clock. Thank you, Joan.
Okay.
Thank you again.
Yes, thank you.
Thank you very much.
Bye-bye.
Okay, bye-bye.
Bye-bye.
Yo puedo seguir los comentarios por el chat.
Yeah. Okay. Thanks a lot.
Thanks.
Okay. Yeah, I see there are no
Hi, Joan. I have a question, actually.
Okay.
Regarding the in learning methods, can we use Lie groups in having the forcing the weight matrices to form a Lie group so that we don't have any singularities in the loss function.
I think I didn't get the beginning of your question. You're talking about
learning methods, using Lie groups in the learning methods.
Okay.
If we constrain the weight matrices to form a Lie group, and we can actually have a representation that doesn't go into singularities.
Okay. First of all, I'm not sure. I don't know because I never did that. But a couple of comments. Yes, if you have a constraint on your data representation, whatever this means, or on your some operators, and this constraint is smooth and it defines some kind of surface, whatever dimension that is and whatever shape. But you must be able to identify the 4 axioms of the group. It's not enough that there is a constraint. That you need to identify if there are some operators and some kind of things. And then if you want to use all of this in a, let's say, practical way, you should be able to find the adjoint and a number of blocks that are definitive for that group. If you are able to do that, then you have a lot of tools available for you. But you have to work these blocks for the particular group that you discover. And sometimes this is doable, and sometimes it's just a nightmare. So the answer is yes, but it depends a lot. Maybe you're trying to do something that it's too complicated, and then it's not practical. It would be possible, but it's maybe not practical. Usually the constraint, there is a keyword that is more pertinent for Lie groups is symmetries. Okay, so rotation is something that when you rotate a sphere, it doesn't change, or translation. If you take a shape and move it somewhere else, the shape is maintained. So this concept of symmetries that is interesting. I'm not proficient on learning, and I know there can be a lot of things inside that. So I cannot give you a clear answer. But bear in mind, you need to discover the axioms, really think about your structure, if it goes well into these kind of things, and then try to identify this little set of key blocks. If you can do that, that's super cool.
Okay, thank you so much.
Yeah, I think we'll leave it here. Please, get to my email and you can write whatever you want, whenever you want. I will try to help you if you are interested. Okay? Thanks a lot.